Okay, so today we're going to be talking about the forest inventory that we conducted at South Nation Conservation. And I'm going to give you an overview of the project to start, sort of a bit of background on LiDAR data we've kind of been introduced to already. But I'm also going to talk about the significance of it being enhanced. Then I'm going to talk about the products that are delivered as part of this project and results of these products. We've gone out and validated this data in the field to see how well it's actually producing the inventory, and we're talking a bit about so why the inventory here? Well, just nearby, we had just finished a successful pilot of, from what I understand, is the first peri-urban enhanced forest resource inventory. A lot of these are conducted by the MNRF using the same techniques, and they do it within forest management. So to have it done in Southern Ontario, and EOMF and OWA, and everything is pretty significant. And there hasn't been an inventory for this area. Well, I rounded up to 40, but imagine the change in forest conditions. And of course, South Nation is experiencing a lot of development, Greater Ottawa area. Communities are growing, and you're losing a lot of forest. Measuring that and capturing. So what's included in the project? Well, we have our enhanced forest resources, and these are just your inventory attributes, and I'll explain that. Part of this does include carbon mapping. So you're able to above ground biomass, and from that, we have a canopy height and canopy cover layer that is going to be useful. Your forest, your woodlands cover, pretty useful tool. Canopy density layers. So from this project, you're going to be able to do habitat mapping based on density of the canopy at certain elevations. So birds prefer a very dense upper canopy, some birds lower canopy, or animals moving through your winter yards and stuff that they provide habitat because it's a dense underlayer. You're going to be able to see that in this. And then we have our forest type information. So this is the area of our inventory. We included the entire jurisdiction of South Nation Conservation. It's a little larger than the actual watershed. That's over 4,000 square kilometers. And what we're using as part of the what makes it an enhanced forest resource inventory is the use of LiDAR data. And Carl already kind of explained, and John as well, the basics of it, but it's just measuring the objects on the ground with as lasers. So you're getting that three-dimensional image of the ground. Because we're using very accurate GPS and sensors that can measure the speed and pitch of the plane, we know where all of these points exist in space. We know the X, Y, Z location of all of these points. So from that, we're able to do extremely accurate measurements. So what you're looking at here is a side profile of the LiDAR acquisition. And you see that the laser has enough energy to penetrate the canopy right to the ground. So you're getting that full three-dimensional structure under the canopy layer. Whereas a photograph can just take a picture of what's happening on top of the trees. With the LiDAR data, we're able to see right down through the ground. So what we do first, because really we're only interested in the trees, is we can remove the topography from the LiDAR data. So the top one that is included, it's just right from the sensor. The bottom one, we subtracted the elevation above sea level. And now that scale on the far left, where the top one is meters above sea level, now on the bottom scale, you see that is just meters above the ground. So now we're able to get tree heights compared for comparative analysis. This is called normalization. So John talked a bit about how we have to calibrate this data to real life. So it is an abstract point cloud. There is points in space. What they mean on the ground in terms of forest inventory? Well, we establish hundreds of these plots. And this is the hard work that the Algonquin Tech students have been doing. They're doing a great job at it. We're going to show you later what's involved in actually measuring these plots, but all you really need to know is that what we do later is we clip out that plot that we measured on the ground. They're 400 meter squared plots. They're circular. We clip it out of the point cloud, and then we take that sort of area of points as it exists, break it down into statistics, and then we can use these statistics in a machine learning, sort of a complex algorithm that can make decisions for you. Knowing what we've measured on the ground, it correlates that with these statistics, and then we can get our basal areas and volumes and biomasses. And then it can predict this over areas that weren't measured based on a similar profile of points. That we know that this collection of points means that in terms of inventory. So now the LiDAR can go out there and find other areas that look like that, apply our real life measurements. So what we're able to do with that is we can now have a full spatial map of our inventory information across the landscape. So on the left, what you're looking at is a traditional forest inventory based on polygons. And the polygons just represent a space on the ground. They're just a shape. But what we do is we average out our inventory information. In this case is the volume of wood that we can sell merchantable. We know that that stand has on average 423 meters cubed per hectare, but we don't know where in that stand. We know it's just been averaged out over the entire area. With the enhanced forest resource inventory, now we're looking at raster features. Rasters are just tiny cells that contain a value rather than a shape, a polygon, which is just a shape on the ground. The cells can show the spatial distribution of volume. So it's the same value for each polygon, right? Or for each, if you overlay the polygon over top, it's still going to be 423 in the raster one. But now we know where there's areas of high volume, like dark area, and then over here there's less volume. So it's a powerful tool for planning how you're going to manage that stand, where could be basal area or heights or whatnot. They're all as grid cells. So here's just an example from the Petawawa Research Forest. On the left is their traditional inventory, and the numbers are the basal area for each stand. So you know that stand has, that particular basal area on average, but where? If you look at that's great, yeah. So yeah, if you look at this one, now we can see using this scale here where there are areas of high BA, where there's high and low BA. But the real benefit is that we've cataloged this entire landscape, right? So we were just sampling here, we were putting in a few ground plots, and then we would have to average that out. We didn't really know how accurate it was going to be because you're limited in how many plots you can actually put in a measurement. Here, the LiDAR has done all the hard work, and it's scanned the entire area and able to produce a full spatial inventory from it. So now I'm going to talk about the inventory for a second. So here's the full extent of the inventory as it's done out in a raster. Here you can see. So you can see on the landscape scale the distribution. This is basal area, so it's the cross section of wood in a given area. For this case, it's a hectare. And you can see, you have a lot of basal area towards there, up here towards the Ottawa River as well. There's some pretty high BA, but in the middle here is where a lot of your agriculture is. Less so, at a landscape planning scale, you can see how powerful it is. This is zoomed in. This is that same layer, basal area zoomed in. So on the left, you have your scale, and now you can see the distribution. One of the main challenges with this project was the LiDAR. Part of the LiDAR was acquired during corn season. So we were able to cut out, usually we just cut out everything below 2 meters, but all of that corn was above 2 meters at this time of year. So we've been busy cutting out all of these fields. Some of these like large square areas with low basal area are But this is just over Larose Forest. Spatial. This is volume, so this is that same layer as volume. So every inventory attribute has its own layer. And so you just kind of lay those on top of each other as you're doing your planning and analysis. And then you can click on any of these grid cells. If you zoomed in, you can click on them and it'll give you that specific value for that grid cell. And that grid cell represents 20 meters by 20 meters on the ground. So for every 20 meters, we can know what that specific PA is. I'll switch to and these are all the inventory attributes that we included as their own layers. So we have our average height, virtual basal area broken up by size class, your quadratic mean diameter, so that's just the average diameter of the trees in the stand, your merchantable volume, which is the volume that has had the top of the tree removed and a few centimeters removed to account for bark. The total volume, which includes all that, so if you're thinking of other products such as firewood, whatnot, that would be included in there. Your volume to basal area ratio, so the ratio of total V bar. So here's the important one here. So we're doing above ground biomass, so all live trees and their biomass from that, we can do species-specific calculations to know how much carbon is being sequestered per 20 meter, well, per hectare in this case. So I didn't do the calculations beforehand. I really wanted to, but I unfortunately didn't have time. But you're going to be able to calculate how much carbon is stored. And with subsequent acquisitions, then we can see how much is actually being sequestered each year, say. I imagine it's a significant amount. Stems per hectare, and of course your habitat. Each one will be its own layer. Switches. So now we're talking about the canopy height model. This is a little higher resolution. This isn't 20 meters by 20 meters. This is every 1 meter. And all it is just the height of the trees above ground. So the color here denotes the height. Darker is taller. Switch this slide here. By the way, these are all from South Nation. Like all these images are from the actual product. So this is just another image I thought was quite striking. This is zoomed in now. So if you were to click on any of these cells, you would be able to get the exact height in meters above the ground. You can see sort of features now, like here's an old portion of a plantation mixed in. You can do canopy gap analysis, so we can measure the gaps. Say there was a disturbance, we can measure that out here. Kind of categorize, we can start doing stands based on height, so we could circle that area and create that stand. But here I've done an analysis. I've just selected all areas of canopy that are above 15 meters and highlighted those in the landscape. And now I've done the understory. So now I've just selected all areas below 2 meters. So now these are the woodlands layers. So now we're moving out of the raster world. We're back into the polygon world, because sometimes polygons are useful for this stuff. All of the data was from after the Derico, was from August of 2022 that we used to get the coverage of canopy. So you're going to have a pretty accurate idea of what your current status is. I don't think there's been too many large services. And we've only included areas of 2 meters and above. So this is your original woodlands layer that was used for planning. I'm not sure when I think it was 2013, or I'm not sure exactly the date that it was finished, but I know it does get continually updated. Now the new one is, see the next slide. You can see the comparison. We've actually gained quite a bit of coverage. I'm not sure why this wasn't included in the original, but LiDAR has picked up quite a few areas that are now a part of your woodlands layer. So you can see the old one here, the coverage over woodlot. Some of the hedgerows weren't included. Next one, the new canopy layer is much more granular. You can see a bit more canopy gaps, and you can see hedgerows. Here's just on top, the blue is the old woodlands layer, and then the green is based on the LiDAR data. So what we used in conjunction with the LiDAR data was called a normalized difference vegetation index. Basically, it's a camera that can detect infrared radiation, so beyond the visible spectrum of light. And healthy photosynthetic plants, photosynthesizing plants, reflect a lot of infrared light, and they absorb a lot of visible light. So when plants aren't healthy, or they're not photosynthesizing, or they're dead, they reflect a lot more visible light. Wood is not absorbing that to photosynthesize with. So this layer allows us to detect, using this index, which is just kind of an abstract number. 1 is very healthy vegetation. -1 is water or roads, things that aren't reflecting as much, or reflecting more visible light. So you can see this is just dirt. These are bare fields, and all of this is pretty healthy vegetation growing up. And we can clip all this stuff out as detected, and that was what is used with the woodlands layer to map out your canopy cover. So you're only getting healthy vegetation. So yeah, it's pretty accurate rather than using photo interpretation. You know that what you're looking at is healthy vegetation. Buildings there in the middle. We can switch this slide. So under our forest type information, so we did establish species plots through SNC to conduct this. We used time series multispectral data. I'll talk about that in a second. All of our species information is from 2021, so it's pretty relevant. We're going down to 10 meters now, so your inventory is at 20 meters, the species are at 10 meters. And we were able to predict confidently these major forest types. We're working on trying to narrow that down a little more. Intolerance is sort of definitive as well, but we're confident we may be able to break up the hardwoods, the maybe maple. We'll see, but I'll show you what we have right now, so get the slide. Just a little bit about multispectral data. So basically, you have light as energy on a spectrum. So you have your UV, your high energy light. If you were to go even further, you need X-rays and gamma rays and stuff that can hurt you. Going this way is your infrared, and then eventually get into radio waves. So here you have your visible light spectrum, and this is not visible. So, well, at least our eyes can't pick it up. But there are satellites that can detect this whole spectrum, and it breaks it up into bands. In Sentinel-2's case, they have 10 bands. There's only 6 here, so there's a few more that are added. And it splits basically each band into its own layer. So green light would get its own layer, red, blue. And when you're looking at color imagery, it's just stacking red, green, and blue on top of each other. The satellite can break up the landscape into tiny little cells, and basically gives each cell a number. And the number represents that wavelength of light, the reflectance of that wavelength of light. Just in a number, like a pretty abstract number, but it's a value nonetheless. And then what we're able to do is just put that into a raster, as the way it reflects light is indicative of the type of species. Each species has a different wavelength that it reflects. Whether you can kind of pick that up with your own eyes or not, the satellites can detect that. So next slide. So what we did was we used time series. So we did a series of months over the same area, and we detected how the light reflecting off the tree canopy changes throughout the year, because there's a phenological difference, meaning like the difference in time, measuring time, and how species change over time. Some species will leaf out earlier in the spring, some species retain their leaves later into the fall or even over winter. So we can measure that and how it changes. So this is April to May, and then May to June, June to July, August, and then we go on to October. And we just layer all of these different time series on top of each other, and then we can do our analysis. The next slide you'll see is our species breakdown. So your red pine plantations, mixed woods, this water feature here. You got your white pine mixed in there, some more white pine stands, hardwood, spruce. This is what the layer is going to look like, and each species will also have its own layer. So you turn it on and off, like you would in like ag maps or mapping applications. this will be great to include in inventory. So you may be wondering how accurate this inventory is. So at this point, we've done a validation based on the data we have, and we measured about 33 different stands. We've gone and actively cruised these stands intensively, so we're measuring on the ground exactly what's happening. And the LiDAR is able to come within 12% of the actual real world value. So this is an RMSC, so that's the error in the value of what you're measuring. So this is an error of 3.81 meters squared per hectare for basal area, which is not bad. That's well within what the MNRF is producing in the FMUs. And to be honest, it being mostly leaf off LiDAR, leaf off LiDAR. The LiDAR was acquired when the trees didn't have their leaves. Is very impressive that we're able to get that. And that's really a testament to the hard work of the students in measuring that really good data that's out there. So yeah, so just in conclusion, you can see from these products, like the project's going to provide a pretty powerful tool to ensure, sustainable forest management is happening in the nation. And that aligns with the purpose of the Trillium Foundation funding to promote resilient and sustainable communities. And it also provides a baseline now. So there will be other LiDAR in the future. I'm sure that will be acquired. And from that, we can use this same workflow to produce another inventory. And now you're starting to get growth and yield calculations and changes in forest cover at a very granular scale. So having this done now is great because now we have a baseline there too. It also contributes to our larger private land coverage, which on the next slide you'll see. Go one more. Where we're expanding after South Nation, where we've done a lot of this is under the same acquisition as Carl was talking about. And what we're able to do is we're able to take the plots we've established here and then add them to the plots we may establish here and create an even better inventory that we can now update SNC as we do these other areas. We can update their inventory with more accurate results because we're sampling more of these forest types that obviously exist in this area as well. So we're going to be expanding out quite significantly. Yeah, that's everything. Thank you guys very much, and thank you to our partners and Forest X.